Welcome to this course on digital system design. In this lecture, we will look at the programmable logic array design. So, we already looked at the fact that programmable logic arrays are devices which are programmable, and using this we can synthesize certain Boolean functions of certain number of input variables. Basically, we write down the functions, set of functions in the sum of product form, and we realize the SOP expressions of the different functions using an array of AND gates followed by an array of OR gates. The AND gates are used to generate the product terms. Later they are being ORed or summed using the OR gates. So, we will have an array of AND gates followed by OR gates. Both are programmable, and that allows us to efficiently design any given functions, certain number of functions for on a certain number of inputs. We will put some restriction of the number of input variables that can be present and the number of functions to be realized. Once we have this, then we can design the come up with a programmable logic array to realize these functions. To recollect, you have a PLA of this form, where we have 4 variables, input variables named as A, B, C, D, and we have 3 functions F1, F2, F3, each function being a function of these 4 variables A, B, C, D to be realized. Then we can write down these F1, F2, F3 as sum of products of the variables A, B, C, D. Suppose the expression for the functions are given by this form, then we can generate these product terms, all these product terms, and then OR it together. So, we need a way of generating such product terms and later to OR them together. So, what we do is we have here vertical lines running for every variable and its complement being present. A bar, B bar, C bar and D bar. And by interconnecting the appropriate cross points, we can be able to come up with any product term. By these are all we have NMOS gates at all these cross points. We selectively remove whatever we don't want. What remains will decide the product term that is being realized. So, here in this case A bar, B and D are being realized here. Similarly, all these product terms are being realized. Then if F1 is an OR of the first 4 product terms, only those are being ORed, we don't OR B, C, and you realize F1, similarly F2 and F3. So, once we put a restriction on the number of the input variables and the number of functions to be realized, then the number of vertical lines are being fixed, because if there are n inputs, we will have 2 into n vertical lines on the input side. Similarly, if there are m functions, there will be m vertical lines which are needed to generate each of these functions. So, given this constraint, the only factor that affects the complexity of this PLA is the number of horizontal lines, and each horizontal line is used to generate one product term. So, the number of distinct product terms that are to be realized will decide the complexity of this whole PLA. So, here there are 5 distinct product terms, and so we need 5 horizontal lines, and the number of cross points is always a function of number of vertical lines and the horizontal lines. So here 8 into 5, 40 are there. Here 5 into 3, 15 cross points are there. So if you want to reduce the number of cross points, because each cross point should have a mass gate, we need to reduce the number of horizontal lines or the number of distinct product terms. So here comes the crucial lesson that we learn, that if you want to realize a set of functions which are all functions of certain number of input variables, when we realize them jointly using a PLA, we are interested in the number of distinct product terms that are present in the expressions for all these functions. We are not interested in only minimizing each function individually. To give more clarity on this one, let us look at 3 functions, f1, f2, f3, which are all functions of 4 variables to be realized using a PLA. So the minterm expansion for these functions are given here. For example, f1 is sigma m of all these minterms. Similarly, f2 and f3. So if you use a K-map reduction technique and reduce f1, f2, f3, this is the result that you would get. Whereas this is the minimal expression for f1, that is the same as this canonical expression, where we have individually minimized the K-map corresponding to f1 and obtained this reduced SOP. Similarly, for f2, we have obtained a minimal expression which is given here, and so on. In fact, I am not showing these individual reductions, but if you do that, this is what you would get. But what we by looking at it we understand is, to realize all 3 functions, we need all these terms. So each term has to be realized. But if one term is replicated, it is enough if you realize it once. So we are looking at the number of distinct terms that are required to realize f1, f2, f3. So if you look for the number of distinct terms in this form of f1, f2, f3, we will see that there is 1, 2, 3, 4, 5, 6, 7 and 8. All these are distinct, because this is BC, this is B dash C, and this is also unique, and this is also ABD and different from A dash B dash D dash B A dash BD. So we need 3 plus 2 plus 3, 8 distinct terms are required. So if you use a PLA to realize this, there will be 8 horizontal lines, and therefore the complexity of the PLA will be larger. On the other hand, if you go in for a joint minimization, wherein we concentrate on the number of distinct product terms being present in the expression for f1, f2, f3, we can reduce the complexity of the PLA. So now you look at the K-map for f1, f2, f3. So normally we would have minimized f1 by looking at this K-map and looking for the largest coverages. Okay. In particular, we will be looking at the prime implicants, and we will only include prime implicants and not just implicants, which means that here this is one 4 square and this is another 4 square, the whole horizontal vertical one, and this followed by this 3 are the one which would have included. Similarly, coming here, there is an 8 square and a 2 square. Here we will have a 4 square and 2 squares. This is how we would have realized it, and that is how the above expression has been obtained. Now, if you are concerned about the number of distinct product terms, what we should do is, instead of individually minimizing it, we should go in for a joint minimization. By that, what we mean is that if a term that is produced for the sake of realizing one function, if it can be reused in the realization of other functions, it is better, because it comes for free, because it is already produced and we can use it. For example, consider this square. If you cover it using a 4 square, then one term will be needed, and we can realize it. That is required for F1. Coming to F2, you have a 2 square that is here. We would try to generate it separately. And coming to F3, you have a 2 square that is present here, which you need. For example, this is also an EPI, essential prime implicant. This is also an essential prime implicant, so you have to generate it. So if you only look at these 3 terms, you would generate 3 terms. One is this EPI, another is this 2 square, and then this 4 square. But now you know, if you have to realize F1, F2 and F3, if you have these two squares already being generated, you can club them together and realize this 4 term. There is no need for separately generating it. Of course, that would be more minimal than the sum of these 2 terms, but we already have it. And when we generate it in the programmable logic array, the number of literals in each product term is not of concern to us, because all literals are already available, and we are indeed the cross points or mask gates are also available. We are only going to remove which is not needed. So we should try to identify common patterns or coverages in these K-maps and try to make use of it. So from that, what we see is, instead of generating this 4 square, we treat it as the sum of these 2 squares and use this. Similarly, if you look at this coverage, so this is one whole vertical 4 square, which will be nothing but A B bar. Instead of generating it, suppose we have this term generated with being an EPI for the F3. If you could make use of that, then we have taken care of these 2 ones already. And the other 2 ones can be accounted for in this term. So we don't need to again account for these 2 ones, because they are already accounted for in a different term. So we use these techniques when we go in for a joint minimization. Similarly, look at this 8 square. Instead of separately realizing it, you can realize it as a OR of this 4 square and this 4 square. So that way, instead of 3, we need only 2 terms. So if you look at only the distinct terms are the following. There is this 2 square, which you could see it's nothing but A B bar C. Okay, because this is A, this is B bar, and this is C bar. And there is this 2 square, which is ABD, and this square 4 square is needed. And having done this one, this we will reuse it here. These 2 things we will reuse it here. This we will reuse it in this one. Then we need this 4 square. That we will reuse it here. So we need, originally we wanted 8 terms to be used. Now we have 1, 2, 3, 4 and then 5. Only 5 terms are enough. So, we could now write this expansion for F1, F2, F3 like this. Although individually the expression for F1, F2, F3 are not individually minimal, they are jointly minimal. You would see that F1 you would sum of this 4 square, 1 and then 2. That is why there were this would be 1, 2, 3 and 4. There will be 4 terms here, and F2 would be this one, that is the middle 4, then extreme 4 and this one, 3 will be required, and F3 will have require 3. But here there are many common terms. Okay. For example, you can see that ABD is common, A dash BD is common, B dash C is common, BC is common. Okay. So, A, B dash, C dash is common. So, there are many common terms. So, only 5 distinct terms need to be realized. So, if you go in for the corresponding realization, this is how it will be: A dash A, B dash D, A, B, D and so on, and they are being and are together to generate F1, F2, F3. So, this kind of an joint minimization is what one look for in realization of the programmable logic array. Now, we need a way of representing F1, F2, F3 in this form and feed it to a programmer to program the PLA. So, we need a representation for this, and that representation is called as the PLA table, where we will tell what are all the terms that are required and what terms are to be ORed to generate each functions. Further, since we have gone in for a joint minimization, the resulting PLA table will be such that the number of horizontal lines will be less, which means that if we have one row, each for one such some product term that is being realized, the number of rows in this PLA table will be minimal. See, each row in this PLA table, which I will explain soon, stands for one product term. Since the number of distinct product term is minimal, the resultant PLA table is called as the reduced PLA table. So, we should always go in for a joint minimization and come up with a reduced PLA table and use it for programming. Well, now, what is the structure of this PLA table? This is the input side where each variable A, B, C, D is written out, and each of these symbols are used to denote what this product term it stands for, that row stands for. So, the first term that we need to realize is A dash B D, and that is what this first row stands for. So, we put a 0 whenever the variable A is present, but in a complemented form. Here the variable A is present as A dash, so we put a 0 underneath A. Then B is present, so you put a 1 because it is in normal form, so you put a 1. C is absent in this term, so you put a dash, which means C is not present. D is present in a normal form, so you put a 1. So, this representation denotes A dash B D. We can easily see that this stands for A B D, that is the next one. Then this will stand for A B dash C dash, and this would stand for B dash C. So, these are the each row stands for one of this one product. On this side, which is the function side, we have one column for each of the function to be realized. Whichever product term is needed to be ORed in that function, you put a 1, and those product terms which are not needed, you put a 0. For example, in the case of F1, the first 4 terms are required, so you put a 1 against all these things. The last one is not required, put a 0. Whereas for the phase of F2, the first term and the not the second and third, fourth and fifth are required. So you put a 1 1 here, 0 0 here. And finally, F3 needs only 3 of the terms, for which a 1 is put against those rows, zeros against those product terms which are not required. So this is how you come up with a reduced PLA table and use it for realization. So this is about the programmable logic array. Then we saw that here we have to program both the AND array as well as the OR array in order to realize it. Programming 2 arrays will make the circuitry very complex. So to make it more economical, we have devices called as the programmable array logic, wherein the AND array is programmable, the OR array is not programmable. What we mean by that is, we assume that each function will be a sum of certain number of terms. Okay? So that many product terms will always be ORed to generate this function. For example, here we put a restriction that the functions are always a OR of up to 4 terms. So these, assuming that 4 terms are available here, they are permanently being ORed to generate the function. Similarly, up to 4 terms can be ORed and generate this one. More than 4 cannot be ORed. That is the restriction PAL puts. Up to 4 it is possible, either it can be 2 or 3 or 4. So this side is not programmed, need not be programmed. It is always ORs 4 terms. A term may have to be realized more than once, that may be present. One for this, one for this. But the advantage here is that this side is need not be programmed. For example, let us assume that we have to realize a full adder using a PAL. The expression for the sum and carry out are given by this. We have 3 inputs x, y and c in, and these are the expressions to be realized. So we have got x here, y and c in here. X bar, y bar, c in bar are all made available. So the first one generates x bar, this is x bar, and this is y bar, and this is c in. Similarly, this will generate x bar, y, and then c in, and so on, c in bar. So like that we generate the terms and then give it to these AND. So what we mean by that is all these are being ANDed together to generate this AND term. Here we need only 3 terms, so we generate 3 terms, product terms, and then OR it. The 4th one is not required, we simply remove this AND gate. So this is a programmable array logic which is more popular as compared to the programmable logic arrays. So PLAs as well as PALs can be used to realize functions of certain number of input variables. More often in a sequential circuit design, or more generally designing a finite state machine, we not only generate functions, we use flip-flops to store the state variables and realize the sequential machines. So, sequential machines has got two parts. One is a state register consisting of certain number of flip-flops where the state variables are being stored. It has certain inputs, certain outputs. Then some combinational circuit which will generate the next state in terms of the present state and the input, and the output in terms of the present state and the state variables, or only the state variables depending upon whether it is a Mealy or Moore circuit. So, more often we also need to use flip-flops. In particular, the D flip-flop is the most popular one to come up with a full-fledged circuit. So, there are circuits which in addition to the PALs also have the flip-flops being present, and they are also a part of the programmable circuits. So, those are called as the sequential PALs. Suppose imagine you have a sequential machine which has got only one state variable or two possible states, which means only one flip-flop is required. It has got two inputs, call it as A and B, and there can be one output. Here we do not use it. And if you want to realize FSM using this one, then the most important thing is the next state variable value has to be realized and given it to the D input of the flip-flop. So, in general, this next state variable value of the next state will be a function of the input and the present state, that is A, B and Q. So, if we may require A or A bar, B or B bar, Q or Q bar. So, what we do is we generate all these literals and use it using a PAL to generate the corresponding next state variable and give it as the D input of the flip-flop. For example, A bar, B, A bar, B, B bar, as well as Q and Q bar are given here. What we have done is we have taken it from the Q bar and used a tri-state buffer, inverting tri-state buffer here also, and to generate this one, buffer to generate this one. So, here is the Q bar comes out, one more bubble will create Q, they are all available. Suppose then if the D input, the next state variable is the following function, let us say it is A bar, B, Q bar, and that is this term, and this term is B bar, Q. So, it is the R of these two terms, and that is the D given as the D input of the flip-flop. If you have one output Z, which is let us say A bar B, we could always use one more such PAL like circuitry and generate an output also. So, a full finite state machine can be realized using this. Here we have shown only two inputs, one state variable and no output. In general, we can have a circuit where the number of inputs, state variables and outputs can be larger. So, here is a circuit which is a commercially available device called as the 16R4 PAL, which is a sequential PAL because it also has flip-flops in it. So, a sequential machine can be realized. What it has 8 inputs that can be fed into it. So, these are the input I1, I2, I3 all the way up to I7. It starts from I believe I0, I1 only, okay. I1, I2, I3, I4, I5, I6, I7, and of course, there is an I8 is also there. All 8 inputs are there, For each one of these inputs, you have two vertical lines going, one for the normal and one for the complement. For example, this would be the normal one. After buffering, the bubble is there. This would be an inverted one. This would be a normal one. This two lines, 0 and 1 line, stands for I1 and I1 bar. Similarly, I2 and I2 bar are available at these points. I3, I3 bar are available at these points. In a similar manner, here is where the other I3s are available. Here I4s are available, I5s, I6, and goes like that. So, if you want to generate any term, we can conveniently tap from either from the normal or the complemented literal of a variable and use it. If a variable is not present, we don't need to use it. Remember, these are all cross points. At all these cross points, NMOS gates are present. What we do is, initially all are connected. All these cross points, the horizontal and vertical lines are connected by a MOS gate. If you don't want, we have to remove that. So, we may end up removing most of them and retain only those which are needed for establishing a connection. So, that is about the input one. Then, about this PAL form. You can treat each one of them as a function, and these one are all functions of up to 7 product terms. You can leave the topmost one. There is 1, 2, 3, 4, 5, 6, 7. So, 7 product terms are being permanently ORed and made available here. And this one can be used to either enable or disable this term. If you enable it, then only it will become available, otherwise it will be tri-state. That can be made available using this point. These points are used for that. These points are used for that. Well, so what we do is, each one of these lines are going to be sum of 7 terms. Each term is generated by these gate. This AND gate generates one term. It runs like this. Depending upon what all you connect, it will generate here. For example, here if you will see that, if you look at this one, it is connected only at these two wherever the crosses are there. So, what you have to do is, to generate one, we have to just AND these two. Similarly, the other one, we have a cross point here and cross point here. Only those are being ANDed together to get these terms. Whatever you don't want, you can remove the if you need only 2 terms, you use that. The remaining are being removed. That is what is being shown here. And we need this term, that is why this AND gate enables this one. And that is, it produces Z, which is an output for this. So, if you want to produce an output which is a function of the inputs and so on, we can always do it. Okay. So, look at each one of them as being fed back. So, you take it and then feed it back here. So, whatever you get it here again goes back and it is available at these 2 points. The reason we will see soon. Then there are 4 flip-flops, D flip-flops, which means each one can store a bit, each one can store a state variable. So, we can realize a finite state machine with up to 16 states. So, again the D input stands for the next state variable's value. So, once we design a machine FSM and come up with the values for the next state variable, use that to program this. Okay. So, you would program this circuit based on that. Well, in the next state variable expression, each one will be a function of the inputs as well as the present state. Suppose you call it as Q1, Q2, Q3, Q4, Q1 plus can be a function of any one of these 8 inputs and the present value of Q1, Q2, Q3, Q4. So that is why what we do is we recirculate Q1s, Q2, Q3, Q4 back to this array, and they are also available while generating these terms. For example, Q1 is being recirculated here. What we actually do is Q1 bar is being taken and the top one is Q1 bar, the bottom one is negated Q1 bar, which is Q1. So both are available. The Q1s are available at these 2 points. And this dot means that it is being reused. Wherever this 2 things runs throughout, so wherever you want to tap, you can tap it and use it for the corresponding expression. So Q1, Q2, Q3, Q4 are being fed back, and together you will see that you will have 2 vertical lines for each one of these inputs, that is 8 into 2, 16, plus 4 state variables. They are being recirculated in the normal and complemented form. 4 into 2, 8 lines in addition will be there. And further, there are 2 here which are just functions that you can realize, which can be used as an output also, or in some other function, which we will see soon. So here there are 2 just functions, and at the bottom there are 2 functions. What you can do is you can realize up to 4 outputs. Suppose you need only 2 outputs, you use only 2 outputs, leave the 2 don't use the other one. So this is what you can do. The final utility of this one is, you may question that, okay, I can realize a function which is an output or the next state variable, but the constraint I have is that it has to be a sum of up to 7 terms. What if I have a function which is a sum of 9 terms? Then what you can do is, you can always generate a function. You can write that into 2 functions, one with 7 terms and one with 2 terms. The one with 7 terms can be realized here, and it can be used as a sub expression for the one with 9 terms. So as such, you can use the 7 as well as the next one to realize any function. For example, what you generate here can in turn be used in the generation of this function. So this function along with this can generate up to 7 plus 7, 14 terms. Expression can also be realized. But of course, if you use this one, this is no more available as an output. Only 3 outputs are possible. So there are some restrictions. Apart from that, we can use this for many ways in which you can configure it. In fact, instead of using it as an output, we can also use it as an input, just like this. So instead of 8 inputs, we can also have in addition a maximum of 8 plus 4, 12 inputs. Or if you want 4 outputs, we have to restrict to 8 inputs, and so on. So there are many ways in which you can use this one. So these are all sequential programmable logic arrays, which can be used for designing very complex circuits. And further they are evolved into FPGAs, which I am sure you will read in a higher course on digital system design. Thank you.